Welcome, everybody, and thank you for attending today's Parasoft presentation on addressing DO-178C, compliance in testing avionics software. My name is Ricardo Camacho, and I'm a technical marketing manager for Parasoft, and I'm also accompanied by Arthur Hicken, our chief evangelist and a good friend. So let's go through some housekeeping. First, everybody's microphone has been muted. However, if you have questions, please enter them into the chat or question dialogue. And if you run into any technical problems, like not being able to hear audio during the presentation, please use the chat. There you can connect with one of our team members who is ready to respond. Okay, let's take a quick look at the agenda. On the agenda, I'm going to start with a quick introduction of DO-178C. It will be a high-level overview of each of the sections of the standard, but I will dive a little bit deeper into Section 6 of the standard since it pertains to testing the requirements and test verification, which Parasoft provides powerful solutions for. I'll also then pass it on to Arthur Hickens, where he makes it real. He will be addressing safety and security for avionics. So it's going to be very interesting, very exciting. Then I'm going to be touching on some of the benefits and cost-cutting options available from Parasoft Test Automation, and then we'll finish it up with the Q&A. All right, so let's get started. I'm going to start with a little bit of a history here. The Radio Technical Committee for Aeronautics, or TCA, was founded back in 1935. They are an independent standard development organization and serve as the basis for government certification of equipment used by the tens of thousands of aircraft flying daily through the world airspace. Now, RTCA is a private, not-for-profit corporation which works closely with the Federal Aviation Administration, so FAA, and industry experts from the US and around the world, such as the EuroK working group, to help develop this comprehensive and also contemporary aviation standard. The original DO-178 standard was released back in 1982. However, it was considered not very useful, then quickly followed the revision DO-178A, published in 1985. The revision focused more on modern software engineering principles, verification practices, and introduced a correlation between critical failure conditions. So you'll have something like level numbers, 1, 2, and 3. So level 1 being the strictest. You may know it better as Development Assurance Level, or DAL. Then in December of 1992, revision DO-178B was released, which shifted from a how-to type of document to what-to-do type of document. So a big focus on objectives that your software process needs to satisfy in order to reach compliance and ultimately certification. Another noticeable change was to the critical failure conditions, or DAL, which grew to 5 software levels and changed to letters instead of numbers. We have A through E, A being the most stringent and E having no safety requirement. Also, testing to your requirements is strongly emphasized. You don't look at the code to create your test cases, you look at your requirements, and it's backed by structural code coverage to ensure that you have covered everything. So DO-178B also incorporated bi-directional traceability of requirements through design, test cases, and down to the code to show that all the requirements have been implemented. And the starter of having tools qualification for use was introduced. Now, today we are at revision DO-178C, which was released in January 2012. And this version will be the focus of the presentation. You also see in this slide the European equivalent from EuroK. This is because the standard has been a continuous joint effort between RTCA and EuroK. DO-178C made a lot of clarifications to remove imprecise wordings found in DO-178B, but the major adoption brought forward was a modular approach to supplemental guidance documents. So for example, you have DO-330, which addresses software tool qualification, DO-331 for model-based development, which is near and dear to my heart. DO-332 for object-oriented software, and DO-333 for formal methods to complement your testing. Now, if you hear of DO-248C, it is a supportive documentation for DO-178C containing clarifications and information on rationale for each DO-178C objective. So additionally, the standards DO-278, now DO-278A, is based off of DO-178C, and it's specifically for ground systems, such as aircraft control systems, which Arthur will be presenting very interesting information on this today. Now, also standards like DO-178C are not just being used for avionics. The military has adopted it for use on other systems. I actually helped test the arresting gear software for the General Ford aircraft carrier to conform to DO-178B level B standard. All right, so let's talk about some of these sections. Now, these are the sections and infographic as captured in the DO-178C standard. I'm going to skim through the sections because it is very comprehensive standard with intricacies that would require actually a lot more time to explain than we actually have. So I'm going to paint in broad strokes. Excuse me. Now, DO-178C is subdivided into 12 sections. Section 1, not shown here, captures the purpose, scope, so how to use the document, provides other document overview points. Section 2 discusses the system requirements allocation to software, where the software system requirements are initially developed and the system operational requirements for customer requirements, and how this information flows into the software lifecycle. Now, one very important part of section 2 is the software level classification or design assurance level that needs to be made. Catastrophic results would be failure to flight control software where the plane would go down and lives would be lost. This would be classified as software level A. Hazardous would be a step down, so serious to fatal injury to a relatively small number of occupants other than the flight crew. This would be software level B. And classification continues to go down to level E, where there is no safety concern if software failure were to occur. Now, the other side of this classification is that with each increased level, as you go from E, as you go from E to level A, there is an increased number of objectives that need to be met. For example, increased traceability and software testing thresholds. And I have actually a slide on this to help explain this. Also, from experience and planning for the future, if your software is classified at level B or lower, you may want to try to achieve some or all of the higher software level objectives. And this has happened in the past when I've worked with projects. You start at level B, and then eventually the customer says, no, it needs to be at level A. And so if you already got a leg up, and sometimes it's really easy to do. So I'll give you an analogy. It's like if you're having your timing belt change in your car and things are already up and dismantled and open, you might as well do your water pump while you're at it. Okay, section 3 discusses the aspects of the software lifecycle process. You are not told what development process to use, but to determine if by the system functionality to be implemented, the complexity, software size, hardware availability, and other attributes. Now, here's the standards example of 4 different development sequences, but it's up to you to decide on what works best for your project. So whatever process you choose, the key is that the standards objectives that must be met are not obstructed by the process. Now, section 4 discusses the objectives and activities at the software planning process, where the production of software plans take place. Table A1 lays it out for you, so let's take a look at actually that table. You can see the 7 objectives on the left-hand side. Documents capturing plans need to be put in place. You have outputs like the PSAC, the SDP, SVP, SEM, the SQA, and the standards that are going to be followed for requirements design, coding, and software verification. In the middle, you can see the software levels and which objectives need to be met based on the assigned software levels A through D. Now, lots of activity happens in section 5. It starts with the development of your high-level requirements. The inputs are the system-level requirements, the hardware interface, and the system architecture. High-level requirements are then decomposed during the design phase, and low-level requirements are developed. Then source code is developed from the low-level requirements where coding standards are applied. Then there is some integration activities, and traceability also does take place here. Traceability is crucial to DO-178C, and the depth of traceability varies based on the software level. So let's step through this very important aspect of traceability. If we look at the traceability that is required for DO-178C level D, we don't care about how the software has been developed, and as such, there is no need to have any traceability to the source code or software architecture. As can be seen here, we just need to trace from the system software requirements to the high-level requirements, and then to the test cases, test procedures, and test results. For levels B and C, how the source code has been developed becomes important. And so we now need to ensure bidirectional traceability from the high-level requirements to the low-level requirements and then to the source code. Finally, for level A projects, there is the need to trace not just down to the source code, but since the source code is compiled into executable object code, then traceability is also required down to the executable object code. This workflow or process can be generally represented with the very well-known V process lifecycle model. So we have thus far described the requirements management that happens on the left side of the V process model, which I'm sure you're all aware of, and that's why I decided to kind of show it in this example. And so the next section of the standard, section 6, covers the right side of the V. Take a look at that. So section 6, the purpose of this is software verification. Is the process to detect, report, and remove the errors that may have been introduced during the software development process. Now, the standard uses the term verification instead of test, because testing alone cannot show the absence of errors. So verification is a combination of reviews, analysis, and tests. Now, there are many verification objectives defined in section 6, and they have been captured in tables A3 through A7 of the standard. You can see here that table A3 shows us the verification objectives for the high-level requirements defined during the software requirements process. As we go through these tables, note that we will be going through different verification levels of abstraction because there are testing to requirements, which themselves, these requirements, are at different levels of abstraction or decomposition. Now, table 4 shows us the verification objectives for the low-level requirements defined during the design phase. Table 5 shows us the verification objectives for the source code and integration process. Table 6 shows us the verification objectives placed on the executable object code or assembly code. So as I mentioned here, this is verification at a much lower level of abstraction. Then table 7, A7, shows us the objectives for the verification of the verification process results. This is done through confirmation of code coverage during test execution, reviews, and analysis. And the code coverage objectives can be at the statement, branch, modified condition decision coverage, and at the object level. Now, coverage of data coupling and control coupling may also need to be achieved, but this is again based on your software level, which includes traceability down to the source code as well. Now that we have quickly gone through the verification sections of the standard and to put Parasoft in perspective, I think this is a nice place to do it here. We offer software verification solutions that addresses many of the verification objectives defined in DO-178, BC, and so forth. as you can see from this infographic. But starting on the left-hand side, we have integrations with ALM tools or requirements management tools like Codebeamer, Polarian, and others that manage the left side of the V-process model. And Parasoft, again, addresses the right side. So it provides the traceability to the test cases and the test and the code, plus the various testing and verification methods for your requirements and at the different levels of abstraction. Static analysis, unit testing, system testing, code coverage, object code verification. We offer all of that, traceability, and actually much more. And I'll cover some of this, and we don't actually have time to cover them all, but I recommend you visit our website and get to look at this yourself and investigate it. All right, going back to this, section 7 discusses the objectives and activities of the software configuration management process. You need to have one. You need to be able to define and control configurations of the software throughout the software lifecycle, have baselines, versioning, change control, change review, protection against unauthorized changes, problem reporting, and more. Now, Table 7.1 and Table 8 of the standard list all the objectives for you, I should say. Now, Section 8 discusses the objectives and activities of the software quality assurance process. The process needs to provide assurance that the software plans and standards are developed, reviewed, and will meet compliance. For example, perform your own audits to ensure that deviations from the standards are detected, recorded, evaluated, tracked, and they're also resolved. And that approved deviations are actually very well recorded, because you may have audits. Now, for certification, a conformity review should be performed to ensure that you have all your artifacts, reports, and evidence. It's all in place with approvals. Section 9 discusses the certification liaison process. For certification, you will want to work with a designated engineering representative, DER, who will evaluate for compliance and act on your behalf towards approval and recommend that the FAA approve your certification. Section 10 is provided for information purposes only regarding the certification process. It mentions the types of systems and equipment that certification applies to. That certification authorities do not certify software as a unique standalone product. They don't do that. It has to be part of the airborne system or equipment. Also, that approval depends upon a successful demonstration or by review of the products produced. Section 11 discusses the data or documentation artifacts that are produced during the software lifecycle, and that the data be unambiguous, complete, verifiable, consistent, traceable. Also, that it be in various forms. You have it in electronic form and also in printed form. Now, these are the artifacts produced during the software lifecycle that I'm talking about. This includes the source code, the object code, the test cases, the results, problem reporting, including your plans, such as plan for software aspects of certification, the software development plan, the software verification plan, configuration management plan, quality assurance plan, etc. Now, Section 12 discusses additional considerations regarding things like the use of previously developed software or already certified software for use on an alternate type of aircraft, or certified software where there is a change in the compiler or processor, and the list continues. But what stands out the most to me in Section 12 is the tool qualification and determination if tool qualification is needed. So if a tool is used that eliminates, reduces, or automates your processes, you have to take into consideration whether the tool might introduce errors into the life cycle. So you will need to determine if the tool being used needs to be qualified. Don't forget that there is the supplemental DO-330 software tool qualification considerations, where the objectives, activities, and guidance is provided. You can see the criteria listed on this slide and the table that maps the qualification level to the software level based on the criteria. TQL1 is the most rigorous level, and TQL5 is the least rigorous level. As the potential impact of the tool on the software lifecycle process increases, the TQL rigor increases due to the potential impact on the system safety. Now, vendors like Parasoft provide qualification kits that automate the qualification process, and this is because DO-178C, the tool, needs to be qualified for use on each specific system. What you need to be careful of is use a tool, go out and get some tool that has never been qualified, because then the responsibility may fall on you to qualify that tool in order to make sure that your system will pass certification. So one of the things I wanted to do was put the key challenges in a nutshell for you when you're addressing DO-178C or B. Note that some of these challenges are triggered based on your DAL or software level requirement. You will definitely need to perform bidirectional requirements traceability. Make sure you have a solid requirements management solution in place. Make sure you know which compliance objectives you need to satisfy and document, and mark them off as you go. Adopt a coding standard and make sure you comply to it. There is MISRA, AUTOSAR, CERT. You may have your own custom or some hybrid of these. Make sure you perform and document your data and control coupling analysis on your code if your DAL or software level requires it. Also, validate on your hardware target. Remember, it's the system that is getting certified. Also, perform structural code coverage to ensure that you've tested all of your requirements. Also, you may need to perform code coverage at the object or assembly code level. Use a tool that has been qualified in the past and that they have a tool qualification kit available to automate this qualification for use on the development ecosystem that you have. And finally, have a compliance management plan and expert DER that can help you through the certification process. So I'm going to be covering some of these capabilities that Parasoft provides to help alleviate or automate these challenges. And like I mentioned, Parasoft C++ test is tube certified, and we have qualification kits, but I'll go through that. So what I'm going to do now is I'm going to be passing this over to Arthur Hicken, he's actually going to be talking about some real life safety and security critical systems that get used every day, which have to pass through some of these standard objectives. So over to you, Arthur.
Great, thanks, Ricardo. And can you see my slides?
No, not yet.
Okay, we give it a sec. It says people can see it.
Ah, okay.
Got it?
Yep, we can.
All right, great. So yeah, so Ricardo has showed us a lot of the really rigorous things we have to do, and it might feel overly constraining, but the truth is that, aviation systems are complex, right? We look at a high level control structure of an aircraft, and we just see lots of interesting things that we would have to test, lots of different scenarios we'd have to take into account. And when we think about what can go wrong, which is what we should be thinking about, we see there's just lots and lots of ways for bad things to happen. And again, in testing, it can be difficult to make all of the various combinations of bad things happen. And so it's super important that we not only test as much as possible, but that we build good software in the first place, because then it's less likely to have a problem when it's under stress, if you will. So the normal way that we go about this is through analyzing what can go wrong, failure modes and effects analysis, for example, right? We look at what can happen. We brainstorm potential failures. What, with the aircraft, what happens if it rains? What happens if there's hail? What happens if there's snow, if there's fog, if an instrument fails, if I have a flat tire? And we sit down and say, okay, well, how do these things happen? What are the causes? What can we do about it? What can for example, in an aircraft, what can a pilot do about it? What can we do about it as a manufacturer to keep it from happening or to respond better to it? And when you're doing these kinds of exercises, it's good to have a healthy paranoia. You don't want to say, well, that's probably not going to happen, so let's not worry about it. You need to really think about what could happen to you. And you need to have a very broad knowledge. You know, if you have, for example, no knowledge of weather systems, then you're not going to do a very good job with potential failures of aircraft systems. So it's great to assemble a team that's reasonably paranoid across a broad spectrum of issues to understand what can really happen. And then you look at these risks that come out of it. Once you've identified, hey, here's the bad things that can happen, what's the severity of the risk? And we saw that with Ricardo a few minutes ago with the 5 different levels based on what happens and can people get hurt? What are the occurrence? What's the likelihood? In other words, can we detect what's going on? Will we know what happens before something really bad happens? And from that, we can start to prioritize. So we say, well, this has a high probability and a high impact. We got to fix it right away. This has a high probability and a low impact, so we should fix it. But it might not be critical. We might not have to ground every aircraft in the fleet for it, for example. If it's low probability and low outcome, then maybe it goes with normal, maintenance cycles. Sometimes we even have to make changes to things. And we've seen that a lot in the airline industry with like jet engine redesigns as changes come about to take into account previously unknown issues. So it's a very complex system, and DO-178 is there to try and make sure that we've done everything we can. So with that in mind, I wanted to look at a security failure and how security and safety actually are intertwined with each other. So I had some fun here with Flight Radar 24, and I recorded the airspace over the greater Los Angeles area, which I happen to live in. So this is last week, I don't know, it was late in the evening, maybe 9 o'clock, run back at 20X. And you can see on the far left there's LAX, right? There's just a bunch of planes doing stuff all the time. But even in different areas, if you look toward the top right quadrant, you see a lot of things going on. There's Ontario Airport out there, etc. And there's just a lot of potential in this area for aircraft interaction. And in fact, I didn't really show it on this map, but at the top there, those are mountains. And some of those mountains are 10,000 feet high, and you get from we're about 1,500 feet here. You get from 1,500 feet to 10,000 feet in a space of a couple of miles. So they can be tricky for air travel as well. So there's a lot of interesting things going on. And one of the ways that we manage this system is by using ADS-B, right? Each aircraft has a transponder that says, hey, I'm going to use the satellite systems and understand where am I at, what's my velocity, what's my direction, and who am I, right? And we broadcast it, and then other aircraft can listen to that and figure out, is this thing in my way? And if it's in my way, alert the pilot. And the really cool thing, the evolution of systems like this is that they go from being like very complex items where you have to look at data and interpret it to really simple advisory items, and sometimes even control items that'll actually have actuators that respond to inputs. So at a simple level, TCAS is one of the systems that we have. And so some pilots like it, some don't. Big aircraft tend to have TCAS or other things like it. Little aircraft may or may not have it, depending on the age, etc., size, the types of missions that it's used for. If it's personal flights for entertainment, it maybe doesn't. In a high traffic area, it seems like a really good idea. The cool thing is that TCAS is designed to try and keep your head out of the cockpit so that you have good situational awareness. So instead of just showing me this graph like I see on the right and showing me, are these planes above me or below me, and what direction are they at, what vectors do we have, what's the distance, what's the speed, how soon will I encounter them, it actually has a really simplistic system. And I encourage you to go watch a video. But basically, if something's within a reasonable zone and potentially an issue for you, it says traffic, which is pretty simple. And now you can pull your eyes back into the instrument panel, take a look. And when it decides that there's something that you need to do eminently, then it'll say something like climb, or descend. So again, it's, the visual display is there, but the audio display helps keep your eyeballs out of the cockpit so that you're looking at the surrounding area. And this is super important as we're going to look here. This system is not secure. It's vulnerable to spoofing. So there's a link at the bottom, or send us an email, or maybe Ricardo, you could like try and cut and paste that link into the chat, or I will later so that people have it. It's a pretty interesting article about a theoretical, this hasn't happened that we're aware of, but there was a team who looked and said, could I spoof this system? In other words, can I set up a transponder on my house and send out data? Now, where I live, I'm 500 meters from a runway of a small airport, and I'm actually probably 50 feet above the airport. So, and I have a pretty tall house. So if I put a big antenna on the roof, I can get pretty good coverage. I could broadcast these things, right? And so when we think about the failure modes for a system, we shouldn't just be thinking safety, we should think security, because when things are insecure, they are inherently unsafe. So one of the basic problems that I often see with people thinking about security is this somehow belief that RF is secure, right? That hackers won't figure it out. If they're on a network wire, then I need to protect it. But if it's just RF, it's okay. Well, RF is unarguably the oldest communication mechanism that was electronic and eminently hackable. So anybody can broadcast it. Did anybody think about this when they built this system? I don't know. It doesn't look like it, right? Basically, there's a couple of different modes that have either an aircraft, a unique address for the aircraft with its altitude and GPS information, or just its altitude without GPS information and its transponder code. They're both, they're unencrypted and they're unauthenticated, meaning when the data appears on my TCAS system, I don't know who sent it. It might say that, it's a 737 flying from Denver to LAX, but it might be somebody playing in the parking lot, right? There's no way to know that the data is really secure. In a normal modern mechanism for communication, we would do something like a public key, private key exchange so that I knew that the data coming was from the individual that it said it was, right? It's part of the confidentiality, integrity, availability triangle, the CIA triangle of security that we talk about. But it's very important, because if you don't know who's sending you the data, then they might be sending you bad data. And what they found in this report is that creating real alerts is perfectly possible. They remind you, and I will remind you, it's very dangerous and very illegal. Don't play with this, right? Like, don't go home and set up something and try to do this. Read the article and enjoy it. I just wanted to walk through, here's a sample of somebody setting up some spoof data. You can do a single aircraft and then, put it in line with another aircraft, because obviously I can sit here in my house and I can look at these things and see what's flying around and then put up my own set of data to tell people. And if there was one plane in front of me, I might be told to, descend or climb depending on conditions. But if I stack up 3 of them, I can set up a scenario that is greater than the performance profile of the aircraft. Therefore, climb is no longer an option and I must descend. So I can start to look at things that I can do. And in fact, I can take a scenario where the aircraft is just tooling along, minding its own business, having a good time, and I could throw a whole bunch of ghost images there that really wipe out the performance profile of the aircraft, where it really can't climb or descend. The pilot, meantime, is getting crazy bunch of alerts, looks out the window, sees nothing. If it's one aircraft and it's supposed to be small and far away, they're hard to spot, right? Especially depending on weather conditions. When there's 7 or 8 aircraft stacked up right in front of me and they're big, suddenly I don't know what's going on, right? And I'm asking myself, what just happened here, right? And what typically happens at that moment is that the pilot turns it off, which leads to a different set of problems. And in fact, there was a related study to the one I mentioned below. It's called A View from the Cockpit, Exploring Pilot Reactions to Attacks on Avionics Systems. So it's a great place to learn more about other potential attacks. But they showed that every attack that they analyzed had a potential for some disruption, which could lead to a reduction in safety. So these possible attacks are real, and I bring it up because you should be thinking about security as part of your safety. What they also found out is that the participants, and I think they had something like 30 pilots where they put them into simulators and perform these attacks. And the pilots had to make a choice between, hey, the system is distracting me. Should I turn it off or should I keep it on? And over a third of the cases, they just turned it off. And again, you can see that if you look back at my previous slide, if the system is just telling you stupid stuff, you're going to turn it off. But if you're in a high traffic area, and even, it doesn't have to be LAX, right? If you get a small uncontrolled airport near a vacation spot and you've got pilots coming in and pilots going out, maybe some pilots doing little tours and people doing their own personal vacation trips, et cetera, there's a lot of, potential for interaction there. So not necessarily just forcing someone to climb or descend or make a turn, but convincing somebody just to turn the system off can also be extremely dangerous. So it's one of those interesting things that once we destroy people's trust, we can really affect safety and security. There's another interesting study that I just wanted to put up, and this comes from the Software Engineering Institute, some research done by them and by NIST. And one of the things that they found is that you can predict security vulnerabilities in code based on software defects in code. And so what we find out is that the underlying coding problems that are associated with software defects, like quality defects, like maybe it's a numeric overflow, which we know was an issue in the 787, right? Or buffer overflow or underrun, which has been implicated in numerous aircraft issues, invalid or missing initialization, null pointers, things like that. These are standard quality issues, especially in C and C++ programming. They also are security issues and safety issues. So it's really interesting, partly because it means that, if you're doing the right thing, you're doing the right thing. But partly it also means that making sure that your software is safe and secure isn't that much of an extra effort than it is to making sure that it's just high quality. So it's not like I'm saying, hey, you were doing quality and then you added safety and now you've got to add security and it's going to triple your work. It's not. It's really based on the same sorts of problems. So with that, I want to turn things back over to Ricardo.
Okay, let me go ahead and switch us. So hopefully you guys can see my screen.
Yes, I can.
All right, fantastic. Now that was very captivating, and I enjoyed seeing all that aircraft throughout LA and Southern California. Thanks, Arthur. All right, so let's quickly go through some of the solutions available from Parasoft in helping you with your verification challenges and goals in achieving compliance and certification. There's the V model that I showed earlier with lots of verification solutions like memory debugging, fuzz testing, API testing. There's UI testing. There's also even service virtualization and actually more that we actually provide. But I'm going to keep it to just a key methods like unit testing and structural code coverage and so on. So really what I recommend is that you visit our website and try out, Parasoft C, C++ test. Click in here. Now, because DO-178 focuses on requirements-based testing, having a strong requirement solution in place is key. It all starts with requirements. So Parasoft has integrations with Polarium, Codebeamer, which have been those tools have been certified. We also have integrations with Jira and others and other tools because it's really crucial that you have that bidirectional traceability to the test cases, the test procedures, the test results, and eventually down to the code. You can also see on the bottom right-hand side, let me go back here, it switched automatically for me, a couple of traceability matrices that help ensure that all requirements have been tested, verified, and validated, that your coding compliance has been achieved, as well as your unit integration system testing that has also been done on your actual target hardware. You can also see on this slide objectives like coverage and reporting, but some of you who are not as familiar with Parasoft, I'd like to explain how our solutions are deployed. So here you see the IDEs So Parasoft solutions have been integrated into the most popular development environments. And we run within a vast set of IDEs like Eclipse, VS Code, Wind River Workbench, Code Sorcery, Code Composer, IR, Workbench, and so on. And we do this because engineers know and are very comfortable with the development IDEs that they're currently using. They don't have to spend days in training and get comfortable with some proprietary tool that is complex and probably looks or is antiquated. The learning curve on adopting and deploying Parasoft solutions are exceptionally short. Your development team will be starting with an advantage and ahead of the game. So this really cuts labor costs and improves productivity and time to market. You know, something else that's really important is on-target hardware verification. This is one of those key objectives in DO-178, and Parasoft supports a vast number of embedded ecosystems. Our list continues to grow as our customer base expands. We refer to this as cross-platform testing, which allows Parasoft C++ test to and test cases to be generated and extended from the host environment onto environments where the software will execute, which might be a target embedded device, a simulator, and I apologize for this. I had this on a timer, forgot to turn it off. You know, and the other aspects to this, which have a slide on this later, is tool qualification. So Parasoft has a tool qualification kit so that our solutions can be easily qualified for use on whatever embedded ecosystem you have in place. Again, this is all part of DO-178 compliance. And we run on simulators, emulators, and other target hardware platforms. Now, Parasoft is a leader in coding standards compliance. We support the complete Cert C and C++ rule set, and this is the same for MISRA C 2012. We are leading in the industry in automotive on AutoSAR C++ 14. We are a provider to primary contractor on the JSF coding standard. We have also been certified by MITRE as CWE compatible. And you see that I have also included DISA, the Defense Information Systems Agency, DISA, which provides a variety of security technical implementation guides referred to as a STIG. Now, that gives guidance for securely implementing and deploying applications on Department of Defense DoD networks. The ASD STIG outlines ways to verify compliance with requirements like application scanning, application code scanning, manual reviews, and functional security testing. Now, our tool suite offers application code scanning through static analysis, specifically supports the ASD STIG requirements for OWASP Top 10. So that's why you see OWASP there as well as buffer overflows, risk conditions, and error conditions. Some of these are often mentioned. Now, the ASD STIG uses a severity category code, category 1, 2, and 3, to organize and prioritize guidelines based on the possible impact of an exploit of the particular guideline. Now, category 1 uses the most critical issues for your team to initialize, place the focus. Now, most items in the ASD STIG fall in category 2. You can visit our website to learn more about these STIG, and actually read some of our collateral that you can download that was written by actually Arthur. So let's talk about some unit testing. With Parasoft, you can automate unit testing to verify your low-level software requirements as well as high-level requirements with integration testing and system requirements with system testing. Your testing is simplified, but we have graphical UI so that users can specify their inputs and outputs and expect the results. Test cases will be organized as you would like, making managing or edits to your test cases very easy. And this execution and verification can be done again on your host and on your target hardware. Now, because of this automation, regression testing is going to be a breeze with the testing infrastructure put in place through Parasoft. Updating your test cases are going to be easy, and you can just simply need to rerun your test cases based on the new code. This is a huge savings in labor and effort and time. And in addition, Parasoft tools can automatically generate test cases for you, expediting the unit testing process, also shortening the testing lifecycle, and again, giving this huge cost savings. Now, another great benefit from Parasoft is that your structural code coverage requirements can be satisfied during your unit testing. Enable code coverage, and as you execute your test cases, the coverage of every statement, branch, and modified condition decision coverage can be obtained. And if you apply structural code coverage during system testing and you execute all your system test cases, the coverage results will tell you how much of the code was executed. Remember that for DO-178, you are using code coverage to also ensure that you have not missed any of your requirements. One fantastic feature called we call it Coverage Advisor, which I have not seen in any other product except for Parasoft, is the capability to tell you what inputs are needed in order to obtain coverage for those really hard to reach lines of code. That's the image that you actually see on the bottom here. I could have used this actually when I was working on obtaining 100% structural code coverage and the arresting gear on the General Ford aircraft carrier. Anyway, again, our automated test case generation capabilities also contribute to obtaining structural code coverage. And these are smart test cases that look for the use of null pointers, test your boundary values, division by 0, and much, much more. So I've been giving you sneak peeks of every slide I had. Now for DO-178B and C level 8, object code verification is a requirement. This is a very time-consuming task and error-prone if you are doing this manually, or I should say through the debugger. That's how you'll end up doing it manually. Parasoft can automate the assembly or code, the object code coverage on your target hardware. Now the reason this is an objective is because when your C or C++ is translated into assembly or object code, and also based on compiler objectives and switches, you may end up with commands that have not been verified. However, Parasoft will literally save you days and or weeks in labor by automating this task for you. And as you know, and I've been talking about this throughout the presentation, tool qualification is a mandated process for safety critical software development in DO-178. Parasoft's tool qualification kits for our C++ test automates the process of creating the supporting documentation required for tool qualification of static analysis, unit testing, code coverage, reducing both the potential for human error and time taken to perform tool qualification. Parasoft automates the creation of documentation required for qualifying Parasoft C, C++ tests for use in safety critical industries by walking the user through an intuitive workflow and generating documentation that's critical for demonstrating tool qualification. And although the process of tool qualification cannot be 100% automated, the unique workflow of Parasoft's qualification kit makes it as painless as possible, reducing manual testing efforts and executing automated tests for selected use cases. I also want to add that Parasoft C++ has been qualified for use in other industries and standards, and that's why I listed them there. We don't just support military aerospace, we support all of these other industries as well. Now, Parasoft also provides a development testing platform where the testing results are analyzed and continuously tracked, which provides process towards achieving compliance. So with Parasoft DTP, the team and management will be able to review real-time comprehensive results on static analysis, code quality metrics, unit testing, code coverage, the process on your testing requirements, your progress. And also, Parasoft DTP, has a very flexible drag and drop dashboard, which we provide over 50 out-of-the-box widgets categorized and color-coded so that you can quickly assemble this on your own and view the quality and progress. Centralized aggregation for verification results makes compliance easier by automatically generating the documents needed to demonstrate compliance. Okay, so let's go ahead, and what we're going to do is we're going to open it up for Q&A. But make sure to follow us. We're on Twitter. We are also on YouTube, Facebook, LinkedIn, and if you want to contact us, you have info@parasoft.com. And And we see our website there, a link so that you can come on board and try Parasoft. So I'm going to go ahead and open things up for questions.
Yeah, so also, Ricardo, I put that link into the chat, so anybody just goes to the chat, you can click on it instead of having to do all that painful typing. Yeah, so anybody's questions, add them to the QA box. That's what we're looking at now. So one of the questions was somebody's concerned about compliance with DISA STIG and OWASP Top 10.
Mm-hmm.
So I guess I'll take that one, Ricardo.
Yeah, I think that's more you.
Yeah, we have static analysis for both of those standards. So yeah, no problem. Yeah, there you go. There's configurations ready to go. Those are both fundamentally around static analysis.
Yeah, and one other thing that I'd like to add is we do support static analysis and also we support for .NET and Java. Be aware that embedded devices, some of them do use Java, and so we do support that tool. So
and there was a question about .NET Core. Someone says they have an app developed in C# but a mandate to upgrade to .NET Core.
Yeah, so so we support .NET, VB.NET, .NET Core. I'm not sure what the difference is, so not sure I want to.
All right, so we'll take a look at it and let you know. Also, we had one around: are there specific coding standards that I should be using for aircraft?
Yeah, so so MISRA, of course, it depends on the language that you're using. MISRA C is extremely popular in the embedded devices and in the avionics. So MISRA is what I would recommend. MISRA C 2012 is, of course, the latest, Amendment 2. So that's what I would use. You may also think about, what are your security requirements. We support CERT. And for C++, I would be recommending AUTOSAR C++ 14. You guys already may also be aware that there is this collaboration between MISRA and AUTOSAR where they're going to be combining and releasing the next support for C and C++ through their union or merger.
Yeah, and that's going to be really nice for people. Next one. I'm having trouble gathering coverage from assembly code.
Okay. So yes, what I recommend is you contact us. We actually have a team here that has developed that particular assembly tool capability. In fact, we are going to be coming out with some material, some training material that we're going to put on our website. It's going to be gated, so you'll need to register if you want to look and access that. But we support it. We support various processors, and we have just a really sharp, bright team that will help you automate that. And so everything I've read and everything I've seen, it looks like the best solution out there. So again, contact us, please, so we can get you in contact with them.
Great. So can you tell me about your qualification kit? Are your tools certified by TÜV-SÜD?
So yes, our Parasoft C++ performs, again, unit testing, structural code coverage, static analysis. It's TÜV-SÜD certified. And because for DO-178, based on your development ecosystem, it'll need to be qualified for that. So we have a tool qualification kit. We have the process in place. We have executable test cases that you can run, and make sure that we provide that you execute all of that with us, and that we can provide you these certificates of qualification. We automate that for you. It's all there available. And for certain other standards, such as like ISO 26262 and IEC 61503, we actually have already been certified. So there's nothing extra you need to do. We just gave you the certification for that. So, but of course, DO-178 is different. So it's all there.
All right. So thanks, Ricardo. That's all the questions that we have. So if you have any others, feel free to email us, info@parasoft.com, or go to the Parasoft website and try it out. And Ricardo, I'm going to hand it back to you.
All right. Well, thank you very much, and everybody for attending. Please look at our website for upcoming webinars, and I appreciate the attendance, and talk to you later. We'll be ending the meeting. Thank you. Bye-bye.